Survival analysis is a statistical discipline that zeroes in on the elapsed time until an event of interest takes place. This branch of analysis is paramount across a breadth of domains, including medicine, engineering, and the social sciences, as it affords a nuanced comprehension of the timing and occurrence of pivotal events. Such understanding is indispensable for the formulation of enlightened decisions and the execution of scientific deductions. The temporal variable, typically denoted as t, serves as the linchpin in survival analysis, gauging the span from an inception point, such as birth, to the advent of a particular event, be it demise or mechanical failure. The nature of these events of interest is manifold, potentially manifesting in a singular or recurrent fashion. In certain milieus, one must account for competing risks, where a plethora of disparate events might transpire, each capable of forestalling the others. Within the realm of probabilistic distributions that delineate these events, we underscore various life distribution representations, each tailored to its specific utilization. The probability density function alongside the cumulative distribution function are instrumental in depicting the distribution of survival times. The survival function, instantaneous hazard rate, and cumulative hazard function provide a profound insight into the risk and mortality trajectory over time. So these precepts lay the groundwork for the construction of survival models and are pivotal for the anticipation and governance of events within a populace or system. They proffer an all-encompassing insight into the mechanisms of failure and the dynamics of survival. The life duration of an individual selected at random, specifically a newborn, can be aptly represented by a non-negative random variable denoted as t sub 0, signifying the time of failure of an entity at the instant it occurs. It is presumed that the entity exists at t equals 0. Therefore, the domain of t sub 0 is those t belonging to the set of real numbers such that t is greater than 0. When we consider an upper limit, known as the limiting age omega, we restrict the domain of t sub 0 to values between 0 and omega. This allows us to model situations where there is a maximum life expectancy or a predetermined temporal horizon. In scenarios where the individual or entity has survived up to a specific age x, we introduce the random variable t sub x, which represents the additional time until failure from age x. It is pivotal to note that t sub x is not identical to t sub 0. However, they are intrinsically related. Understanding this relationship is fundamental for advanced analysis and survival studies. In our voyage through survival analysis, we encounter the failure density function, a statistical concept that permits us to quantify the likelihood of failure at a specific instant in time. This function, denoted as f sub 0 of t, is defined as the limit as the time interval approaches 0, providing an exact measure of the failure probability in the immediate vicinity of a time t. The failure density function is a potent tool that fulfills two essential conditions. Firstly, it is never negative, which ensures that the associated probabilities are always sensible. And secondly, the integral of this function over time equals 1, guaranteeing that the entirety of the probability is distributed across the temporal scale. When the random variable of age at failure, t sub 0, is modeled with a distribution that includes a shift parameter a, the conditions for the density function are adjusted to reflect this shift while maintaining the integrity of the distribution. The concept of safe life emanates from the analysis of the hazard function, signifying that for a positive a, the possibility of failure before reaching this point is 0, This stands in contrast to the concept of in-use aging, where no safe life is assumed and failure can occur at any moment. The lifetime distribution is an essential instrument in survival analysis and is represented through the cumulative distribution function f sub 0 of t. This function aggregates the probability that an event of interest, such as failure or death, occurs at age t or earlier, for an entity that commences its existence at time 0. It is assumed that the probability of failure at the outset is null, that is, f sub 0 of 0 equals 0, reflecting the impossibility of failure at the very commencement of existence. This function is also non-decreasing, which ensures that the accumulated probability of failure will never diminish over time. It can only remain constant or increase. Furthermore, its continuity indicates that there are no abrupt jumps or discontinuities in the probability of failure, thereby avoiding predictions of catastrophic events that would affect everyone at the same time. The cumulative distribution is intrinsically connected with the failure density function, f sub 0 of t, which is obtained as the derivative of f sub 0 of t. This relationship allows us to understand the failure density at any given moment. The integral of f sub 0 of u from 0 to t gives us back the function f sub 0 of t. Completing the connection between these two fundamental measures, for continuous variables, the following numerical equivalences are established. The probability that t sub 0 is less than or equal to t2 is equal to the probability that t sub 0 is less than t2, which is equal to the probability that t sub 0 is less than or equal to t1 or t sub 0 is less than t2, which is equal to the probability that t sub 0 is less than t1 or t sub 0 is less than t2. In other words, the probability of failure within a specific interval is constant, regardless of whether 1 includes or excludes 1, both or neither of the interval's endpoint. In actuarial notation, Q sub 0 equals F sub 0 of t is the probability that T sub 0 is less than or equal to T. Q0 equals F sub 0 of 1 is the probability that T sub 0 is less than or equal to 1. It's important to note that when the value is equal to 1, the subscript is omitted and not written. This is the standardized official actuarial notation. In our survival analysis, we utilize the survival function S sub 0 of t, which offers an intuitive approach to understanding the likelihood that individuals will survive beyond a specific time t. This function is essentially the counterpart of the life distribution function, f sub 0 of t, and is defined as the probability that the time to failure t sub 0 is greater than t. The survival function and the failure density function are intrinsically linked. The former is obtained by integrating the failure density over the interval from t to infinity, and the latter as the negative derivative of the survival function with respect to time. These relationships are not only mathematically elegant, but also provide a deep understanding of the dynamics of survival over time. The fundamental properties of the survival function established that at the beginning, at t equals 0, survival is complete. That is, S of 0 equals 1. This reflects the life expectancy at the start of the study period or at the beginning of an insurance policy. As time advances towards infinity, the survival function approaches 0, which signifies that eventually failure or death will occur. It is the certainty of our mortality. The survival function S sub 0 of t is not only monotonic and always decreasing, but it also satisfies the integral of the failure density over all time equal to 1. This is crucial for actuaries who calculate life reserves and ensure the sustainability of long-term insurance plans. In our study of life duration and failure events, the concept of the percentile plays a crucial role. The percentile, denoted as T sub p, refers to a specific point in time when the accumulated probability of failure, expressed by the function f sub 0 of t, reaches a certain value, p. This function is monotonic and increasing. Hence, its inverse function, known as the percentile or quantile function, always exists. For a random variable t sub 0 with a life distribution f sub 0 of t, the first moment, known as the mathematical expectation, is defined as the integral of t multiplied by the failure density function f sub 0 of t over the entire domain of t. This provides the expected value of t sub 0, which is a measure of central tendency, commonly referred to as life expectancy or the mean life. The second moment of t sub 0, which provides information about the dispersion of the variable around its expectation, is calculated in a similar manner, but by squaring t before integrating it with the density function. To gain a more complete view of the distribution, we can calculate the higher order moments, which offer us finer details about the shape of the distribution. These are calculated by raising t to the power k and then integrating with the failure density function. It's important to highlight that for these moments to be finite and therefore useful, the limit of the product of t to the k by the density function must tend to 0 as t tends to infinity. This condition ensures that the variable has finite variance and that the distribution is not too heavy-tailed at its end. This is proved as following. We consider the integral from a to infinity of t raised to the power k times the survival function s sub 0 of t with respect to dt. This integral is assessing the coth moment of the survival function over the range starting from a. Integration by parts is applied to this integral. The result of this is typically a subtraction of two terms. The first term is the survival function, evaluated at infinity and a, multiplied by t, raised to the power k over k. And the second term is the integral from a to infinity of t raised to the power k times the negative of the failure density function of sub 0 of t with respect to et. We then take the limit of the first term as t approaches infinity. This involves evaluating the survival function s sub 0 of t raised to the power k over k at infinity and at a. We subtract the latter from the former. The second term, which is the integral of t raised to the power k times the failure density function f sub 0 of t, remains. This term is necessary to complete the evaluation of the kth moment. The assumption is that the survival function s sub 0 of a is equal to 1, which simplifies the expression. As t goes to infinity, the term involving the survival function times t raised to the power k should approach 0 for the moments to exist, which means the moments are finite. This ensures the variable has finite variance and is not overly heavy-tailed. To simplify this result, we have to solve the limit of the survival function over t raised to the power k. We begin by considering the limit as t approaches infinity of the survival function s sub 0 of t over t raised to the power k. This examines how the survival function behaves as time extends towards infinity, scaled by t to the power k. We have to apply L'Hopital's rule, since we have an indeterminate form of the type infinity over infinity. By differentiating the numerator and the denominator and taking the limit, we obtain the rate at which the failure density function decreases relative to t to the power of k plus 1 as t approaches infinity. The expression simplifies to the limit of k times at raised to the power k plus 1 times the failure density function f sub 0 of t as t approaches infinity. Here we're looking at how the term t to the k plus 1 affects the failure density function's behavior as t grows without bound. The final line states that for the kth moment of the survival function to be finite, the limit of t raised to the power k1 times the failure density function f of x must tend to 0 as t approaches infinity for all k less than infinity. This is based on the initially stated property that as t tends to infinity, to the k1, times f of x must approach 0 when k is finite. Two special cases for a lifetime variate with a equals 0 are the following: the life expectancy and the second moment of the random variable t sub 0 can be calculated in terms of the survival function. Therefore, to find the average lifespan, we integrate the survival function over its support. The mean life is equal to the area beneath the survival function. Finally, we get an expression for the variance of the random variable t sub 0. The force of mortality is a fundamental concept in survival analysis, represented by lambda of t, which measures the instantaneous rate of failure or mortality of an individual or technical unit at a given time t. It is an essential indicator for monitoring the functionality of a unit and its probability of failure over time. The force of mortality stems from the concept of conditional probability. The probability of A given B equals the probability of A intersect B divided by the probability of B. For a random variable representing the age to failure denoted as t sub 0, and defining events A as t sub 0 is greater than t and B as t sub 0 is greater than t plus y, the conditional survival function is the probability that the t sub 0 is greater than t plus y, given that t sub 0 is greater than t, equals the survival function at t plus y divided by the survival function at t. This ratio provides the conditional probability of surviving beyond an additional time. Y, given that survival has already been achieved to time t, utilizing the survival function evaluated at t plus y and t, the conditional event that t sub 0 is greater than t plus y, given t sub 0 is greater than t, can be transformed into t sub 0 minus t is greater than y, given t sub 0 is greater than t. And the corresponding conditional variable y is called the future lifetime or remaining lifetime of a survivor. The conditional survival function of y given t sub 0 is greater than t equals the survival function at t plus y divided by the survival function at t, which is called the conditional survival function. Its complement is the conditional lifetime distribution function. Differentiating the conditional distribution function, f of y given t sub 0 is greater than t with respect to y, gives us the conditional failure density. This simplifies to the failure density function at t plus y divided by the survival function at t. The probability that t sub 0 is less than t plus delta, given t sub 0 is greater than t, is approximately equal to the failure function f sub 0 of t sub 0, given t sub 0 is greater than t times delta, which simplifies to the failure function at t times delta, divided by the survival function at t. This is an approximation of the probability that a survivor fails within the small adjacent time interval at t. Now, the failure rate is deduced as delta goes to 0. Lambda of t equals the limit as delta approaches 0 of the failure density function f of x given t sub 0 is greater than t divided by the survival function at t, which simplifies to the limit as delta approaches 0 of the failure density function at t plus delta over the survival function at t. And this ratio tends to the failure density function at t over the survival function at t. This result is called as force of mortality or the hazard rate function. In other words, for a small increment in time, delta, the conditional probability that the survivor fails in the time interval, t plus delta, is approximately equal to the product lambda of t times delta. Another possible interpretation of lambda of t is the rate at which failures occur per unit of time relative to the portion of the population that has not yet failed. If one wishes to predict the probability of failure at age t for a newborn or a technical unit with no history of failures, one should use f sub 0 of t. That is, f sub 0 of t is an unconditional predictor of the risk of failure at t. When it is known that a unit has survived up to a t, then lambda of t should be used, which is a conditional predictor. Comparing numerically f sub 0 of t with lambda of t, it is observed that f sub 0 of 0 is equal to lambda of 0. F sub 0 of t is greater than or equal to lambda of t for all t greater than 0, since s sub 0 of t is less than or equal to 1 for all t greater than 0. There is a fundamental difference between the force of mortality, lambda of t, and the conditional failure density, f sub 0 of y given t sub 0 is greater than t. Lambda of t is a function of t, the age reached, while f sub 0 of y given t sub 0 is greater than t is a function of future lifetime following a given age, t. Both lambda of t and f sub 0 of t sub 0 is greater than t are non-negative, but lambda of t is not a density function since it is not normalized. On the other hand, the integral from 0 to infinity of the force of mortality equals infinity. In this way, the force of mortality is an instantaneous failure rate if and only if it satisfies the following properties. The force of mortality is greater than or equal to 0 for all t, greater than or equal to 0, since the failure density function is greater than or equal to 0, and the survival function is greater than 0. Then the force of mortality equals the failure. Density function divided by the survival function is greater than or equal to 0. The integral from 0 to infinity of the force of mortality equals the negative integral from 0 to infinity of the derivative of the natural logarithm of the survival function evaluated in t, which is equal to natural logarithm of 1 minus the natural logarithm of 0. Therefore, it equals infinity. Thus, it is proven that the integral of the hazard function over time diverges, implying that the probability of eventual failure is 1, which is consistent with the properties of a survival model. In reverse, it is possible to express the failure density function, the lifetime distribution function, and the survival function of a population in terms of its force of mortality. By integrating the relationship of the force of mortality, we obtain the integral from 0 to t of the mortality force, mu sub u, with respect to u, is equal to the negative natural logarithm of the survival function, s sub 0 of t, plus the natural logarithm of the survival function, s sub 0 of 0, which simplifies to the negative natural logarithm of the survival function, s sub 0 of t, because s sub 0 of 0 is equal to 1. By exponentiation, this transforms into the survival function. The survival function, s sub 0 of t, is equal to the exponential function of the negative integral from 0 to t of the mortality force, mu sub u, with respect to u. Thus, the lifetime distribution function, f sub 0 of t, is equal to 1 minus the exponential function of the negative integral from 0 to t of the mortality force, mu sub u, with respect to u. Finally, by differentiating, we find the failure density function f sub 0 of t in terms of the mortality force mu sub t is equal to the derivative with respect to t of the life distribution function f sub 0 of t, which is equal to the mortality force mu sub t times the exponential of the negative integral from 0 to t of the mortality force mu sub u with respect to u, which is mu sub t times the survival function s sub 0 of t. Lambda sub 0 of t equals the integral from 0 to t of mu sub u do. And it satisfies three conditions. Lambda sub 0 of 0 equals 0. The limit of lambda sub 0 of t as t goes to infinity equals infinity. Lambda sub 0 of t is increasing. It's easily obtained that the survival function s sub 0 of t equals the exponential function of the negative lambda sub 0 of t. And also, the lifetime distribution function f sub 0 of t equals 1 minus the exponential function of the negative lambda sub 0 of t. Conversely, we have the following relationships between the failure density function, lifetime distribution function, and survival function on one side, and the integrated force of mortality on the other. Lambda sub 0 of t equals the negative natural logarithm of the integral from 0 to infinity of f sub 0 of u do, which equals the negative natural logarithm of s sub 0 of t, which in turn equals the negative natural logarithm of 1 minus f sub 0 of t. Unlike the Mofasa of mortality mu sub t, which can be intuitively interpreted as the conditional probability of failure in an infinitesimal interval, given that no failure has occurred up to t, the cumulative force of mortality lambda sub 0 of t cannot be interpreted in this way. Lambda sub 0 of t is not the sum nor the integral of conditional probabilities since the conditioning event changes with t, and there is no law of probability that leads to lambda sub 0 of t. Therefore, lambda sub 0 of t does not possess a probabilistic connotation. We hope this video has enhanced your understanding and appreciation of the beautiful interplay between mathematics and real-world applications. If you found value in our discussion, please like, share, and subscribe for more content that bridges the gap between theory and practice.